Condensed structures seemed really fun, and they are pretty good. But the most challenging things for students are the oxygen-containing functional groups in condensed structures. Take this molecule right here. How are we going to turn this condensed structure into a Lewis structure? Okay, so first, let's make sure we have the right number of valence electrons. So we have carbon, we have 3 of them, 1, 2, 3. So 3 times 4 equals 12. We have an oxygen for 6 electrons equals 6. And then we have 6 hydrogens, 1 each, 6. So that's 24 valence electrons. Okay, so just looking at this, this condensed structure, until you get the hang of it, can be a little bit ambiguous. So if I saw this and I was trying to convert it to a Lewis structure for the first time, I might draw something like this. Okay, so we've connected them in a line, that's good, but how do we get everything its octet? I guess we could theoretically draw lone pairs there, lone pairs here, but will that really work? So let's think about that on two levels. Will it work in the sense of, does this look like a very stable structure? If you've been doing all your Lewis structure practice, you'd note that a carbon with 2 lone pairs would actually have a 2- charge. That is not going to be stable. So that's the first kind of red flag. Anytime you see 2- on one atom, something is wrong. Okay, secondly, 24 valence electrons. How many do we have? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we have too many valence electrons. What we've done in the past, when we get into that problem, is we have created a double bond. So let's try that. Okay, create our double bond there. Now we're thinking, okay, this looks a little better. We have the right number of valence electrons, but are we really the best that we can be? Because we want to be the best that we can be. Looking at the structure, it's not ideal. If there are charges on condensed structures, we have to show them. And there aren't any charges there. But if we look at this structure, oxygen with only 1 lone pair of electrons is going to be positively charged, and carbon with 1 lone pair of electrons is going to be negatively charged. So there would be some charges on this condensed structure if this is the actual structure. But it turns out that there aren't any charges on this structure. So that's actually one thing that maybe we should have drawn on the previous page. On page 19, it says drawing organic structures made easy, condensed structures. Another bullet point to add to that page is that condensed structures show charges. So if this was the condensed structure, we would have to have a negative and a plus right there by those 2 atoms. So this can't be the condensed structure. So what are the other options? It turns out that when there's a carbon and an oxygen, it might be that both of these atoms are actually attached to that carbon. So let's try that. So instead, we can continue our CH3 like we had it, and we'll draw it out because we're doing a Lewis structure here. So CH3, then we're going to C. Now if we put the oxygen just bonded to the carbon, because both of these are attached to it, then we draw a CH3. Now we have a structure. Let's add electrons to give everything a full octet. Now let's count up our electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Great. Everything has a full octet. Everything is neutral. So this is a perfect Lewis structure from this condensed structure. So again, not that one, it's that one. Okay, there are 3 more on this page 20 of ours. And the first one, the next one is CH3, CHO. So I want to give you guys a minute to think this one through and then come back to the video. So pause it, try this with this, because really I promise you this is something that really challenges students, both in Organic Chemistry 1 and Organic Chemistry 2. And the more time we devote to it now, the simpler it will be later. So boop, you paused it. Now you're back with us. So we have CH3CHO. Remember I said when an oxygen comes close to a carbon, often both atoms after that carbon are attached to the same carbon atom. So if we wanted to take that shortcut, we can draw this CH3 all as one unit, and we'll draw our C bonded to our oxygen and bonded to our hydrogen. If we just add electrons, we have a few problems, right? Because this is going to be negatively charged there. This oxygen would be negatively charged there. Also, maybe we've used too many electrons. So again, pause the video, see how many electrons we've used, and see if that matches up. Boop, boop. All right, we're back. So there are 2 carbons, that's a total of 8 electrons, 4 hydrogens, so 8, 9, 10, 11, 12, plus the 6 from the oxygen would bring us up to 18 electrons. And here we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we've used 2 too many. What do we do when we do that? We remove electrons from adjoining atoms and make a double bond between those 2. So this would be the Lewis structure for that condensed structure. Okay, let's do the final 2. The one also next is CH3, CO2H. So this one, again, the stuff after carbon is all attached to it. So again, it's going to be something like this. And again, let me stop for a second. Do it yourself. Pause, unpause. You can even fast forward to see what I did after you try it yourself. But you're going to get the most out of this if you try it yourself before you see what I do. So do that first. Please. All right. You've already done it. Good job. And you already succeeded. This would be that one. Let's put our lone pairs in. Okay, so that is the 3rd one. The 4th one looks pretty similar to that. We got CH3, CO2, CH3. So again, pause, do it, come back. What's this one going to look like? Unpaused. There it is. There's all our condensed structures. Like I said, these do definitely give students the most trouble. So just remember, if it's neutral, it's got to be neutral. Remember to draw them out, check your lone pair electrons to make sure your charges aren't off, and then go back and see, do we have the right number of valence electrons? So if you do all those things, you're going to just crush condensed structures, and you're going to love them so much. All right, great.